This video would be absolutely deafening.
Yeah, I used that on Thursdays, actually.
Oh yeah?
Yeah, it was a little wacky.
Uh-oh. Well, anyway, I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day, and I thank you again for these students. Just ask you to bless this class today, Lord. Help us to understand a little bit more about your creation together, and help us to glorify you in what we do, Lord. In your name I pray, Lord Jesus. Amen. All right, so I wanted to work through an example of the LU decomposition technique. And this is just like a little kind of trick calculation. So just kind of follow along with me as we do it, and then we'll see if we can do another one together, all right? So start with this matrix, and I'll explain what the LU decomposition is once we get to it, all right? But basically all we're going to do is just do row reduction. So like row 2 minus 3 row 1. All right, and that brings me to the matrix, 1 minus 1, 1, 0, 0 minus 3, 2, minus 2, minus 3. All right, but then here's where it gets weird. Don't write 0 there, actually. I'll do it in a different color. But what we do is we put a 3 there because we subtracted 3. All right, I know that's weird, but that's it. All right, put a parentheses 3 there like that. Next up, we do row 3 minus 2 row 1. All right, so 1 minus 1, 1. The 0 and the minus 3 here stay the same. And I'll leave that blank because it's going to be, let's see here. 0 here as well, and minus 5. So just an ordinary row operation, but here's the wrinkle. Instead of putting the 0 you cleared out, first of all, we keep that 3, okay? Once that's there, it just stays there for the rest of this. But this, because I did minus 2 times row 1, I put a plus 2 here, okay? And I know this may seem like dark magic at the moment, and that's fine. It should seem like that. I'm just showing you the trick. And then, let's see here. We're almost done with the forward pass. Actually, are we done with the forward pass? Wait, what? Oh man. Just a second, guys. I feel like I lost the plot here somewhere. Huh. All right, well, I wasn't expecting this, but then again, I don't do this too often, so anyway, let me trust my notes. I was smarter when I wrote these notes. Let's see here, so row 3, minus 5/3. Oh, I see. I got to get rid of this. I'm sorry, I'm an idiot. The next pivot is this 3, right? So I got to clear out below it. So it's row 3 minus 5/3 row 2, all right? Now, if I hadn't been writing the red stuff, if I just been keeping zeros, it'd probably be more obvious to me what's going on. Like right now I'm just doing the forward pass. That's all that's going on, forward pass, right? So 1 minus 1, 1, my 0, my minus 3 here, my 0, and now, all right, so go to my other color so you guys can see what I'm doing. So I've got this, and you guys, if you're starting to notice the pattern, you guys tell me, what should I put here? Positive 5/3, right? Notice the sign flip. The sign. Oh, it's unpleasant. So, fun story. My son swims, they all swim. And so my wife bought them shorts, like the jammers for swimming at some point, back in July. Daniel's had this bag of shorts that the shorts came in the bag, and the bag has had the shorts, and the shorts are black, and the bag is clear plastic. But at some point, I guess Daniel noticed a fly flying out of the bag, which was a little bit disconcerting. And upon further and closer inspection, he realized there was a rat in the bag. Not a living rat, mind you. A deceased rat. And it's been there for some time, like since July. And he's just been carrying this bag back and forth from swimming practice. Every so often I get in the van and I go, it smells bad in here. What is that? I believe it was the rat. So, despite the fact that we were past the window of returns for Amazon, they did give us a refund. So, if you ever get shipped something with a rat that you didn't ask for a refund. It's the moral of the story. I don't know what this has to do with this, but anyway. So, and then of course my son has to show me the picture of he has it like I'm trying to get like water for coffee, and like in my face it's like right here. Look at this, Dad. I was like, no, I don't want to. I don't want to see that. Anyway, you guys had lunch already? Okay. All right, so here's the deal. This is so basically, just to recap, we do the forward pass. All right? But keep, parentheses comments in the places you ought to have zeros, right? And I don't mean all the zeros. There's no parentheses thing here, right? I'm talking about the zeros that you cleared out by the sweeping with the forward pass, all right? Okay, then here's the trick. L is equal to, you heard that too? Okay. I tried to recreate it. Something along the lines of, because people online can't hear it, so somebody's got to do it. So this is the L, you put the identity, like so, and then the parenthetical numbers, they appear up in here. So you got yourself a 3, you got yourself a 2, and, oh my bad. Wait a minute. Oh, I did that wrong. That was supposed to... Oh, because this is based on R2, this is not where it goes. I'm sorry, guys. I knew something felt wrong. It's supposed to be here. That was supposed to be 0. The parentheses appears... Where you put the parentheses has to do with what row you put here. Since I put a 2 here, I put it there. Since I put a 1 here, I put it here. I had a 1 here, I put it there. All right, that's the pattern. Okay? Do you guys see what I'm saying? I'm messing with row 1, that's why I put the 3 here. I'm messing with row 1 again, that's why I put the 2 here. I'm using row 2 to mess with row 3, that's why I put the 5/3 here, okay? That's the pattern. Anyway, the point is, you got this matrix here with zeros. This is, of course, a lower triangular matrix, right? And on the other hand, I can write down U, 1, -1, 1, 0, -3, 0. That's just taken from right there, right? And then 0 is everywhere else. And the magic of the LU decomposition is that if I multiply these two, I should get LU. Let's try it out. multiply these, we get 1, 3, 2 for my first column. I get 0, excuse me, minus 1, minus 3, minus 2 for my second column. And I get 1, 0, I think, and 1, oh, excuse me, 2 minus 5, which is minus 3. I sure hope when I look up that's A. Whew. Okay, it worked. Yay. Yes?
When you put the 5/3 in column 2,
Uh-huh.
what if in row 3, column 2, it wasn't 0? Would you put it, or is it always going to be 0?
It wouldn't, like if it wasn't 0, I wouldn't have been doing that row operation. I don't know, it depends on what it was. But, the reason that we're over there at this point is because there was no pivot in the second column. So the pivot's in the third column, which is why we skip past that in some sense. But in the other sense, that 5/3 goes there, right? All right, so if we understand this, right, we should be able to do this for another matrix, right? So this is, by the way, the LU decomposition. So you can take a matrix if the forward pass doesn't involve a permutation. If it doesn't involve a row swap, then doing this thing I just showed you, we'll find a matrix, a lower triangular matrix L, and an upper triangular matrix U, such that L times U is equal to A. Now, this is actually useful for, like, schematically. If you think about it, suppose you're solving, A times X equals to B, right? But that's actually LU X equals to B, right? If we call this right here Y, then you'd have LY is equal to B. And Ly equals to B is way easier to solve. Like for this one, for instance, if I was solving, AX equals to, let's say, 1, 2, 3, just for the sake of example. So what I'm saying is I could instead solve Ly equals to 1, 2, 3, all right? But what is Ly? Y is equal to Ux, right? Making that substitution. But Ly, check it out, right? It's L was, or did I? Just a second, guys. Let me not so fast. Yeah. Okay, so Ly is 1, 0, 0, 3, 1, 0, 2, 5/3. Can you solve this system? We can solve that super easy, right? Top down, yeah? Like, we don't need row reduction here. We just need some common sense, right? So, like, okay, so let me erase the proof that it works for a second so I can do the algebra here. So, like, this gives me y1 is equal to 1, right? And my second one is 3y1 plus y2 is equal to 2, which tells me that y2 is actually equal to what? -1, very good. And then finally my 2y1 plus 5/3 y2 plus y3 is equal to 3 tells me that y3 is 3 minus 2 plus 5/3, I guess. Solving for y3 here, because I know y1 and I know y2. So if I did make a sign error here, so that's 1 plus 5/3, 8/3, yeah? Now, okay, so we've got my y, quote unquote, is 1 minus 1 8/3, right? what's my solution? Well, I go back to my substitution, right? Y equals ux. Oh man, I still don't have it directly, do I? Oh, I guess I still have to work. So that's equal to ux, but u was what? 1 minus 1, 1, 0, 0 minus 3, 0, 0, 0, right? But I guess that's nice because we can see from this immediately that what? X, minus 3x3 equals to what? Minus 1, right? So therefore x3 is 1/3. And I guess once you know that, whoa, dude. Hold on a second. This example is not as exciting as I thought. We have 8/3 equals to 0 equals, oh man, bad example, I'm sorry. So at this stage we find out there's no solution because that last equation's inconsistent. That has to be a possibility, right? If you set a 3x3 matrix equal to a constant vector, right? And that constant vector is not a linear combination of the columns, we learned that we can't solve that problem. There's no way to build this vector from taking a linear combination of these three vectors. Well, not this one, my bad. There's no way to build the 1, 2, 3 vector from these guys because it just so happens that these are not independent. In fact, it's pretty obvious that the first one is minus, the second one is minus the first one, right? So there's something missing in 3 dimensions. And one of the things that's missing happens to be the 1, 2, 3 vector, which is why we couldn't solve the system. Use your imagination. And if you think about it, if this was a bigger matrix, right, that was more convoluted, this would actually be kind of nice because you can solve the Ly equals to a constant problem pretty quickly. And then once you know the solution to that, you can go and solve the ux equal to the constant problem pretty quickly. This is and so that becomes more useful if for some reason you already knew L and U for other reasons. Right? In engineering, there's applications where you happen to know L and U because of like design of a circuit or something, like some kind of shunt circuit or something like this is the place where it happens. But anyway, I just wanted to share with you the magical algorithm because it's kind of cool. There's like, there's the LU decomposition. There's also something called the QR decomposition. And there are others that are basically a special way to pick apart a matrix into, representative pieces. This just has to do with the forward pass. Like the L and the U matrix, the structure of the L matrix just has to do with what's required to make the forward pass. This pretty much encodes in it everything we did for the forward pass, right? And we don't even have to do the backwards pass to find the LU decomposition, which is kind of neat, Okay, so if we understood this, let's try our hand at doing this for a other example. But I wanted to make us think less, so I printed something out for you guys, if I can find it. Oh, here, attendance sheet, yay. So like, I need one. You can have one. Take one and they'll pass them around, yeah. So here is a particular matrix. And what I want to work together with you guys on is if we can figure out the LU decomposition of this one too, just to try to add some. I figure if we can do this together, then you guys probably pretty well understand the LU decomposition, right? And I figure with this printout, it should keep us out of trouble, right? And I'm going to try not to write everything on the printout out. I just want to use the printout to figure out what is the LU decomposition. So we'll look at it together, and we'll try to identify. This website's great, by the way, right? This website actually does the forward pass first, and then does the backwards pass, right? So we ought to be able to use these steps to just straight up construct the L, right? So let's try to do that directly. So let's see here. So L is going to be LU. So how big is L and how big is U? This is a 3x4 matrix, right? And so I think it's going to have to work into like a 3x3 times a 3x4, if I remember right. So I'm expecting that we're basically using the 3x3 identity matrix and trying to add some stuff here. Let's get nuts. What do we got here? What's the first move? Minus twice the first row to the second row, right? So I believe that means we should put a 2 here, right? And then we add minus 1 times the first row to the third row. If I understand correctly, that should put a 1 here. Oh, zounds. Interchange. Oh, I was trying to avoid that. Oh, phooey. All the luck. Well, let's ignore that and see what happens. Rats. Let's just try to ignore it and see what happens. Multiply the second row by minus 1. Oh, phooey. Well, this is all this has gone very badly. All right, we're going to bail on this example. I tried. The alternative is to have a discussion of the PLU decomposition. This is one of my weaknesses. Let us not do it. I have tried this in the past. It goes badly. Unless I'm super prepared, which would not be the case at the moment, obviously, because this is not what I wanted. All right, fine. Let's make up another matrix and we'll try it. We just, anyway, save this row reduction. We can use it for something else some other time, right? All right. But in the meantime, let's just find another matrix which behaves. The thing is, it's not that complicated if there's a permutation. It's just like you have to, there's an extra step, and I'm not 100% certain on how the slick algorithm plays out for the when there's a permutation. My notes say it, I just don't trust it entirely, unfortunately, because I have a bad memory. Oh, come on. All right, so in the website, if we go, come on, here, remember, wrong linear algebra, right? Let's do this one. Up here at the top, we've got this matrix calculator site, so let's go for, we're going to try for 4x3 again. Wait a minute. I can't do 3x4, right? And here we go. Please don't be all right, is there any permutation in here? I see no permutations. I think we're, yeah.
So what's the advantage of this? Because if we're already doing the first pass, like we can solve the matrix.
Oh, the advantage is being able to find the LU decomposition for a matrix. It has other purposes besides just solving a system. I was merely showing you, the application to solving a system is all. Yeah. In terms of what its purpose is, that's a larger question that, I don't have a complete answer to off the top of my head. Like I said, there's like connections with circuit analysis. If you look at a particular design of circuits, this comes up. But, all right, so this one here, we have, my A is what was it? 1111. 2200 and 1123. Okay. All right. So again, I believe that it should be a 3 by 3 L. And all right. So what's the forward pass? Minus twice the first order of the second one. So I think I put a 2 here. And minus the first to the third. So I think I put a 1 here. And multiply ignore this. Well, let's see here. Rats. I want to not do those row multiplications. So we'll try this. This may have messed up my hope. Minus 1 times the second row to the third row. Minus 1 second row to the third row. Minus 1. Phooey. I guess I just got to do them. Okay, so this is row 2 minus twice row 1. I think we can do these both at once. Row 3 minus row 1. That gets me 1, 1, 1, 1, 0, 0, minus 2, right? And 0, 0, 1, 2. Thank you. So I don't want to do what he did. I want to just use this and do row 3 plus 1/2 row 2, I think, because that will get rid of this. Oh man, seriously? One? I think it's a 1, right? But if I keep track of, I'm not fine. If I do the parentheses thing, what should I have up there? And I go to the trouble of printing this thing out and everything. It just blows up in my face. But I get for trying to be prepared. I tell you what. What's that? Yeah, I think that so like here, this puts a, there's a 2 here, right, and a 1 here, and then over here, what you said, is it go here? No, here, right? Yeah, you said minus 1/2. We'll find out soon enough if we're right? What was here?
0, 0.
All right. So I think that's it. So I think that puts a minus 1/2 here. And if I'm right, the U is 1, 1, 1, 1, 0, 0, minus 2, 0, 0, 0, 1. And we can check. Is L times U equal to A? I sure hope so. Wait a minute. So I'm just having a moment of, can I multiply these matrices? That's not a good thought to have this far into this. Let's see here. Yes, we can multiply this. This is a 3 by 3 times a 3 by 4. These are multipliable. And what do we get? 3, I think. Ah, all right. Woo. All right, it works. All right, so I hope that demonstrates the process for you guys. You have my promise to not ask you to find the LU decomposition when it requires a permutation. Like, it's not much more to learn that, but this is where the course gets to, and I think it's enough, you know? So, with that, let us go on. For the next topic is definitely more important than this. I'm just spending more time on this because I think it takes more time to understand what I'm saying, you know? I think you really need to see a couple of these unwrapped. And by the way, if you read the notes, I do explain why this works like it does, but it's just kind of a trick, a shorthand for a much longer theoretical discussion. And so if you want to see that theoretical discussion, it is in the notes. I do explain why we're doing what we're doing in terms of elementary matrices and the inverse of elementary matrices. It's much akin to the arguments we've gone through in previous lectures. But I figured you guys have had enough of the elementary matrix arguments in here, so maybe I should just show you the algorithm, which is what I did today. All right. But the next topic is determinants. What is a determinant? And a good answer to that probably is, well, a determinant, what is a determinant? Well, the determinant is a volume, is probably the right answer to that question. So it captures the volume of vectors is really what it's doing. So like, but of course we need to define it. So to start with, the determinant of like A, B, C, D is defined to be AD minus BC, right? This is the definition of the 2x2 determinant. Notice that we had A, B, C, D. The inverse of that was what? Remember this? I mean, I hope so. Otherwise, the surprise attack mission didn't go well for you today. You didn't know this, right? This was kind of it. One of the problems was just this, right? So when does the 2x2 inverse exist? Right. AD minus BC is not equal to 0. And that kind of already gives away the main story here. Spoiler alert, the point of the determinant is if it's non-zero, the matrix is invertible. This is manifestly true in the 2x2 case. The formula makes sense if and only if the determinant's non-zero. It turns out this is generally true. A matrix is invertible only if the determinant is non-zero. But I also was just telling you the slogan, the determinant is volume, right? So what I'm telling you is if you were to imagine a little like parallelogram with side vectors, you know, AB and CD like this, all right? And if you can go from AB to CD by a counterclockwise rotation, like this, if this is actually the picture, then the area of this little parallelogram is the determinant. And if the determinant is negative, what does that mean? If the determinant's negative, what that means is my picture is wrong. Actually, this vector isn't up here, it's down there. And there's like a clockwise rotation from the first row to the second row in order to get the area. So it actually is the signed volume, right? By the way, that formula is not obvious. You had to play around for a while to derive it. Next up, the 3x3 determinant. So A, B, C, D, E, F, G, H, I. I guess I'll be boring and do that. You know what? Let me not do that. I take it back. Let me put numbers into this. I think it's more useful if I do that, actually. Can you guys tell me anything else about the 2x2 case before I go on jibber-jabbering about this one here? What if we transpose the determinant? Would that change anything? I mean, the matrix that we're taking the determinant of. Yeah, look at it. It wouldn't change it, would it? Like if you calculate the determinant, notice that the determinant of the transpose would be what? It would be A, C, B, D, right? It's still AD minus, BC. So in the 2x2 case, we can already see that the determinant of A is equal to the determinant of A transpose. This is only, obviously, a 2x2 determinant proof, but it turns out that what happens in the 2x2 case happens in the n/n case, actually. The proof that it's true for the n/n case is not as easy. But don't worry, this is not proofs class, so you're safe. Anyway, so the usual thing is to do Laplace's expansion by minors. I'm going to expand on the top row. So you do A11 times the determinant of the stuff without 1 in it, which is 2, 2, 3, 3, 2, 3, 3, 2, 3, 3. Okay, so that's the stuff without 1 in it, right? And then minus A12, the determinant of the stuff without 1 and 2 in it. So we're looking at a, that's not quite true, is it? I guess that's just a quirk that it has no 1 in it. This one's got no, well, anyway, I'll just write down one. I put A21, I'm going to do some color coding here in a second. I'll explain to you what's going on. A21, A23, A31. Now, if you had Calc 3, some of you have, some of you haven't, I think. It is the formula for the cross product, essentially, but this is a number, not a vector.
Yeah.
But it's the pattern for the cross product, absolutely.
Well, the cross product gives you, well, I guess it does give you a vector.
Yeah.
But you can find the magnitude of it.
Sure.
You know the scale.
That is true. Where was I? A13. So we've got A21, A22, A31, A32. Okay. So the way this works, guys, is like for the middle one here, right? I'm getting these guys and those guys. That's what I put down here, right? Basically, I'm crossing out the second column and the first row and picking up what's left. That submatrix forms that subdeterminant. But that's it. That's the definition of the 3x3 determinant. Well, okay, I wouldn't say that's the definition. For me, this is a theorem. If you'd like to know what I think the definition of the 3x3 determinant is, well, here's the definition of the n/n determinant. The determinant of A is equal to the sum I1, I2, da 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 da, IN, epsilon, I1, I2, da da da, IN, A1, I1, A2, I2, da da da, AN, IN. This is, and here, this thing is epsilon 1, 2, 3, all the way out to n is equal to 1, and it's completely antisymmetric. In other words, if you flip any two of the indices there, you get a -1. If there's any repeat, you get a 0. So this only contains either plus or -1, depending on plus or -1, provided that the indices I1 through IN are distinct, the distinct collection of the numbers 1 through n, put in some order. But that for me is this is how I define determinant, guys. But you don't have to define it that way if you don't want to. Certainly this is not part of the required portion of this class, but nevertheless, if you're interested, That's a stone cold formula for determinant that you can prove all the properties from. And by the way, the same thing you can use to define the determinant, and this would be the cross product that you guys are talking about, A cross B. Here's a formula for that. It's the sum over ijk, epsilon ijk, A sub I, B sub j, x hat sub k. This right here is a formula for the cross product in the same light, and it shows you why the determinant and the cross product are part of the same, well, bloodline, I guess. Right? It's the same animal. The thing that binds them together, that makes them what they are, is this completely anti-symmetric symbol, this epsilon ijk. In 3 dimensions, epsilon 1, 2, 3 equals to epsilon 2, 3, 1 equals to epsilon 3, 1, 2 is equal to 1, whereas epsilon 3, 2, 1 equals to epsilon 2, 1, 3 equals to epsilon 1, 3, 2 equals to minus 1. These are the 6 non-trivial terms that form the cross product with plus, 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 and minus, minus, minus. Search your heart. You'll find that this is true. This is exactly the pattern that you saw in Calc 3 if you saw it. If you didn't see it, it's okay. We're not in Calc 3 anymore. But if you are in Calc 3, then you remember the 3 by 3 determinant also has to do with the triple product, right? Remember this? The determinant, if I put vector A, vector B, vector C, that's equal to A cross B, right? Dotted with C. This triple product gives you the signed volume of the parallelepiped, right? I can't draw this thing worth anything, but and again, it's plus if you take A cross B, if I'd done it right. Like as it stands, A cross and B is down. So this actually, this triple product would give you minus the volume of that parallelepiped because if I take A and I cross it, and if I take A and cross into B, my thumb is down, but C is the opposite way, which means that this triple product would be negative. But anyway, it gives you plus or minus the signed volume. For example, if your 3 vectors are coplanar, the determinant works out to 0 because the volume that they subtend, using them as legs of a solid, is 0. Anyway, any questions? I don't know. So I think most of you have had Calc 3 before, is that right? Who has not had Calc 3? So if you guys don't know what I'm talking about, that's fine. I'm just trying to connect with what they know because, like I said, determinants are volume, but how do you know about 3-dimensional coordinate geometry, right? Unless you've had Calc 3. Well, I know the answer, Minecraft, right? Or the Roblox, or I don't know. Perhaps the Night Fort, I don't know, but there are many things. But you're like, I know all my 3-dimensional reasoning from Meta, said no one. Let's see here. Anyway, what's Meta? Oh, so let's work some out. You notice that this minus here, it's maybe catching us off guard, but it's there, all right? So all right, so let's calculate the determinant of 1, 2, 3, and we'll just, we'll do 2's in the second, and then 5, 4, 0, there we go. All right, so this gives us 1 times the determinant of 2, 2, 4, 0, minus 2 times the determinant of 2, 2, 5, 0, plus 3 times the determinant of 2, 2, 5, 4. So you guys help me out. What do we do here? Then we go back to our 2 by 2 determinant, and we've got 1 times 0 minus 8 minus 2 times 0 minus 10 plus 3 times 8 minus 10, which gives us minus 8. Uh-oh, what'd I do?
Is the second term in the right-hand side of the equation correct? Would it be determinant of 1350, or would it be 2250?
It's 2250.
Okay.
Oh, where's that coming from? Great question. So I'm expanding on the top row about this 2, so that picks up these guys, which is why I wrote this, the 2.5, the 2.0. That's fine. Do feel free to ask. It's cool. So plus 20. What's 8 minus 10? Minus 2, right? Minus 6? All right. And so what do we got? We got 20 minus 14, 6, right? That's, I mean, the geometric significance of this is if I took, like, this is my 1, 1, 2, 5 vector, right? And then I lay down this back here as my, 2, 2, 4 vector, right? And then I go up from there, like with a 3, 2, 0 vector, right? If you can imagine doing such a thing. Oh well, I tried. My pictures are deteriorating. Anyway, the volume of this thing is 6. If I could draw it worth anything. So that's one of the significances of this. Let's look at this a really different way. Determinant of 1, 2, 3, 2, 2, 2, 5, 4, 0. So my default, guys, is to expand on the top row, but we can actually expand the determinant along any row or column. So let's try expanding on a column instead of a row. Yes, sir.
In the previous example, is it a coincidence that the first 3 also add up to 6? The first 3 indices in the vectors?
Probably coincidence, yeah. But I mean, I think that's probably part of the reason we got the 6 there is because there's 6 and a bunch of stuff I'm doing. I managed to get like 6, 6, 6 in my Calc 3 test today by accident. Like the cross product of 2 vectors worked out to like 6 minus 6 minus 6 or something. I was like, oops. But anyway, the pattern here, guys, goes like this: plus, minus, plus, minus, plus, minus, plus, minus, plus. This is the guide for expanding the subdeterminant formulas. So like what I'm saying is if I expand here on this 2, 2, 4, the rule, I have to be guided by this, is I do minus 2 times the determinant of the things that's not paired to that minus 2, namely, sorry, I gotta think. This 2, that 5, 2, 0. And then I do plus 2 determinant of.
Would you use the top and bottom row if you're using the middle row?
Yeah, so this 2 here.
So would it be 1350 for the first one?
This 2 gives me those guys. So I've got 1, 3, 5, 0. This minus 2, it's that top, that I'm expanding on the top 2 there. I really should have all different numbers for best effect here, but it's too late. So that 2 is this 2, and this is this. This is this one. This guy is that guy. And this one is this one. That's the pattern here. And then finally I got to 4, but I got to put a minus because the plus minus rule. That's Laplace's expansion by minor. It comes with these plus minuses, like it or not. If you remember Calc 3, the minus on the y term is inescapable. It's there. Ignore it to your peril. Same deal here. So the 4, I got a 1, 2, 3, 2. Well, 1, 1, then 3, then 2, then 2, I believe. All right, so then this is like minus 2 times minus 10 plus 2 times minus 15 minus 4 times 2 minus 6, which is 20 minus 30. Plus 16, also known as 6. Yeah, okay, good. Math is funny that way. It doesn't matter what your life story is, or if you're bringing an authentic voice to the calculation or not. Truth is the truth. No matter how you slice it, it will get back to 6, right? Sorry, there's no postmodern mathematics.
Does this only work for square matrices?
Is there a determinant for non-square matrices? No. So yeah, we need square matrices. If I was to answer that question more adventurously, I would say perhaps. And maybe the answer to that is the wedge product. Because I can take the wedge product of just 2 vectors. I can take the wedge product of just 3 vectors. I can take the wedge product of as many vectors as I like. And basically the deal is this: as long as those vectors are independent, the wedge product is non-zero. But if they're dependent, if they're multiples of one another, it's 0. Same thing happens here. If the determinant has a repeated row or column, 0. So let's try that on for size. Example 4, what if you're up against the determinant of 1, 1, 1, 1, 1, 2, 2, 2, 2, 2, and then 37,001 pi e natural log of 2. What's your favorite number? Square root of 17, 0, 8, 9, 67. The answer is 0. And the reason for that is this is minus the determinant of 2, 2, 2, 2, 2, 1, 1, 1, 1, 1. Let me call all of this stuff Pac-Man. See, the determinant is constructed so that the interchange of any row or column, if you swap any row or column, you get minus what you started with. You see, so if you have a repeated column, when you swap, you're back to minus, you get minus what you started with. And so if you think about that logically, that must mean the thing is 0. Well, anyway, we don't need to write all that. I'm cluttering it up. It's 0. The answer is 0. We don't need all this. 0. Ooh, that didn't sound right. Because of the repeated row. Furthermore, there's a whole laundry list of tricks for determinants you want to calculate. Like, okay, yes, the expansion by minors thing, sometimes we have to do it. It's unavoidable. But if we can avoid it and use tricks, it can be very helpful. One of the other tricks is that the determinant is, let's see here. Sorry, I'm thinking. So here's a theorem for you guys. The determinant is not changed by like additive or the additive type row operations. If I subtract one row from another, it doesn't change the determinant. So, you see what I can do? If I just subtract twice row 1 from row 2, I get what? 0, 1, 2, 3. I subtract 6 times row 1 from row 3, I get 0, 1, 2, oops, 3, 0, 1, 1, 1. At this point, I can stop. This is equal to 0. Why? So, additive row operations do not change determinant. Why is that one 0?
Because the transpose has a repeated column.
The transpose has a repeated column, great, but agreed. But we also have a theorem, if there's a repeated row, it's 0. So you can just say that. But, so you're like, very good, very good. I see where you're going there. But yeah, it's just this, repeat, 0. All right. Example 6, if I have time. So like the first order of business, right, is we need to get up to speed on how to calculate determinants. And a lot of you, if you've had Calc 3, you've got a little bit of an edge here because you've done the cross product, so you kind of already have some sense of what's going on, but there's really no substitute for just working some problems. So here's my last example. All right, so if I got 0, 2, 0, 0, 0, 3, 0, 0, 0, 0. Let's see here. 4, 5, 6, 0, 0, 7, 8, 9, 10, 0, and finally, I don't know, 1, 1, 1, 1, 1, there. What I would do here is I would go, well, that's minus the determinant of, I flip the top to flip these. So the other trick I want to tell you guys about is if we flip a row, if we just permute a row swap, that gets you a minus. All right? So you get a minus from swapping rows. Yeah, minus from swapping rows. And so what I'm left with here, 4, 5, 6, 0, 0. I'm not doing anything to the lowest 3 rows, okay? But in this case, this matrix is a matrix of a very special type. This is a lower triangular matrix. Guess what? For lower triangular matrices, there's a beautiful thing that happens. The determinant works out to, you just multiply the diagonals. So the answer is 3 times 2 times 6 times 10, also known as like 360. So the answer is 360, but it's not 360 because I've neglected to keep track of my minus. So the answer here, minus 360. What does that mean? That means in 5 dimensions, if you build the 5-dimensional solid with these as the edges, this guy, this guy, this guy, this guy, and this guy, the volume of that 5-dimensional solid happens to be minus 360 because, well, the minus is because of the orientation of the sides, but not that we really care so much about orientation in 5 dimensions, but there you go. Anyway, I hope this gets us started. I will hopefully finish sharing with you the tips and tricks next time, but anyway.